I said that my watch is to determine and see what happened and start adjusting these parameters. The second doctor, known for his eccentric and whimsical personality, played a crucial role in the series. Yes, but could you clarify? Done. I have this here. Is it okay? What does it do? This is supposed to be the engineer who comes to adjust the monitoring protocol. If I have a protocol for the dance breast met or a protocol for it, usually the breast protocols are the same and fixed, meaning the key values are known. And there isn't much variation because you are using the target frequency and the frequency filter. So it starts to set these protocols on the machine itself and begins to say, I want a certain signal to noise ratio. The signal to noise ratio, which is your image quality, represents how much signal you see compared to the noise present in the image. The SNR has specific values that are available on the machines. Who adjusts them? The applicator comes in and says, for example, I want to set the signal to noise ratio to 1. What does 1 mean? It means a ratio of signal to noise of 1. No, I want the signal to be higher than the noise, so I set it to, for example, 1.5, 1.3, or whatever. So what parameter gives me that value? What are the factors that give me this value in a certain kV and a certain milliampere? So who makes the adjustment for this? The automatic exposure control. There are two ways. Either the protocol is already set on the machine. So when you or the operator selects the desired SNR, or the protocol itself is set to this value, it knows. It will work at a certain kV and a certain milliampere. If I want a dense protocol or a dense breast, I need to increase it to achieve the signal to noise ratio, which is a unit. I will set the thick breast and the thin breast to give me the same signal to noise ratio, but the thin has a lower parameter and the thick has a higher parameter. So what do? I will say that the milliampere here was such that it corresponds to the thick breast at this level, while it corresponds to the thin breast at that level. This is set on the protocol on your monitor on the machine and is adjusted and accurate, and it works on it. So the automatic exposure control gives the exposure automatically to the sensor. I start by making adjustments to the signal to noise ratio and the energy I want, along with the factors I need. It stops the exposure, meaning the first time it detects an incident, it reads and starts to say, now I have reached the number of photons or the energy I want, so I will stop. When it stops the scan, it stops the exposure. This happens in no time. I'm not saying this takes time. It occurs in less than a second in some cases. I'm not saying it's all handled by something called a pre-exposure. It takes an image, and before that, it takes another image. The image it takes is very low dose, but it knows the attenuation amount. Previously, I mentioned that there is something called calibration. Calibration means what? It means that you are supposed to have a baseline. You are supposed to have two meanings. The specific thickness will give you a certain attenuation. If you increase the thickness, it will give you a different attenuation. So he has an equation that he knows. The specific thickness should yield a certain attenuation. If I took a picture and it showed me an attenuation of this amount, he will plug it into the equation to find out how much thickness he has, and then he will adjust the parameters based on this information. Are you okay, doctor? Yes, I'm fine. Are you fine or not convinced? No, I'm fine. This is what I mentioned about imaging just now, that it takes it, but it is not used. In imaging. No, it is not used in imaging. But he knows the extent of what happened. What more than that? Is there a question? Someone's here? He is currently speaking, but the audio is not working right now. Dr. Hani, do you have a problem? We can't hear you. The issue at hand is primarily due to the internet connection. Omar, who is currently residing in Egypt, is experiencing this problem. Ben Egypt's Beshozel. The moving intensifier grid is used in normal mammography imaging. And regarding magnification, I said I have an air gap, so I don't need to remove the magnification factor of 1.8. The magnification factor of 1.8 is simply the distance from the source to the image receptor distance over the source to object distance, which is stated as 1.85. This is the topic of the magnification factor, and this is considered fixed for me. Now, regarding the point I mentioned to you, the problem is that if there is thick breast tissue or high density material, there are three solutions. One of these solutions is to use an ionization chamber. This ionization chamber is something that is used in dosimetry to measure the ions formed as a result of exposure, meaning the radiation in the air. There is an ion ratio that comes into existence as a result of its interaction with air molecules in the environment, resulting in the creation of both negative and positive ions. The chamber itself is made of a particular type of gas, and when this radiation impacts upon it, it generates negative and positive ions in the process. This particular process allows for measurement in the designated region. It subsequently begins the process of assessing the degree of solidification and subsequently aids in addressing the complex issue of halting at a relatively minimal quantity of emitted photons or energy particles, which ultimately fails to achieve the desired optimal imaging result. This is precisely the point where automated fusion control mechanisms come into play, and as previously mentioned, it involves the strategic approach of adopting a pre-exposure methodology. The idea is that he should essentially know the attenuation and start adjusting his parameters appropriately and accordingly. There is also another option in order to effectively rely on the fluorescent screen, meaning when we were talking about the screen, or in the screen film, specifically this will be with the screen film radiography. As we were talking about the fluorescent screen, or the screen film radiography, you have a screen. When radiation falls on this screen, an interaction occurs, and you get the light output. The amount of light photons that will be generated here will be quite large. In this case, it indeed tells you that the solution is to use the fluorescent screen, which will provide you with a significant number of light photons. These light photons can be relied upon, and the beam hardening will not affect them even if the incoming radiation is high. The percentage of incident radiation is low, but it will be a lot of photons for me, and it relies on them for forming its image. The last option is to change the detector used and use a type of detector called solid steel detector, which we will discuss in posted detail. The mechanism in the detection process relies on something called scintillation or scintillator material, specifically sodium iodide. Sodium iodide receives the material, which is referred to as sodium iodide. The radiation is received and it contains scintillator material. This scintillator material is the same concept as PSP. Phosphorus here is not functioning. Why is it not producing this electron? This electron comes out and returns to its phase, and then it starts to be used. The idea is that it is essentially trying to adjust this mechanism so that it does not terminate the examination before its scheduled time. It relies on another technique or method to measure the number of photons coming in or the energy that will fall on its sensor. Here is the dynamic target and dynamic filter. This is the amount of attenuation. The red part indicates the amount of attenuation that occurred when I used the dynamic filter. All of this has been removed from my curve. So you have a part here that decreased and a part here that decreased. What I have to work on is the part that has maximum intensity, which is this part. This is what I worked on in imaging for me using the dynamic filter. And this part about the rhodium again, compression and its benefits, reduce scatter, spread tissues, and reduce geometric unsharpness because the patient will not move, thus decreasing the blurring effect and geometric unsharpness as it keeps the tissues closer together. Reducing movement unsharpness relates to the focal spot size in the case of large and small formats. It's usually like this, God willing, that the mammography work doesn't have any additional information beyond what has been said. I may have added some things that weren't in the FRCR physics notes because I don't rely on just one source. I'm not only working from the FRCR, I'm taking part of the questions from the FRCR MCQ physics and seeing where the questions are going and what people are discussing, so I can start incorporating this information. I also work a bit from force physics, taking some things from there. I believe this is comprehensive work. I will examine other things if there are things I can add. If there are some things that I would add to the questions, if there are some things that I would add to the questions, if there are some things that I would add to the questions, if there are some things that I would add to the questions, if there are some things that I would add to the questions. I mean, for example, I can explain it again if there is something among the questions, because sometimes I see things in the questions that I don't fully understand. So I focus on them to ensure they are included. If something is not understood, it would be better for someone to communicate with me. There is no movement on this matter. Dr. Islam, if you please, regarding the...
But could you please explain this part to her regarding mammography?
Okay, I wanted to ask you about this topic. It's available? Yes? Go ahead.
About the new version. I mean, the version, now. I have settled. I mean, I am working on it.
It mentions Hussein, the father of children, in a series.
Sure, no problem. If you could send it to me, I would appreciate it because I was going to add the part about the stereotactic biopsy as well. If you want to discuss it, that's fine. I have no issue with that part. It's not a big deal. It's just a part, but the idea is that I have even worked on it. We were working on the machine and they perform something called using a specific needle, where they do calibration on the machine first with the dimensions and measurements to make the biopsy automatic. The idea is that first it performs calibration by entering the dimensions for the machine and the needle, and then the machine starts to come in, and what happens is that we will enter the exact location, meaning the location of the sample or the biopsy that will be taken. The machine itself is assembled in such a way that it has a needle, and all of this moves automatically to the location, and then the gun is activated, and the needle starts to descend into the exact spot. All of this happens automatically. This means that all of this happens automatically. You or the doctor just need to specify the location in a certain way. You set it on the machine and tell it, for example, that you want this point and nothing more. Then it starts to move and reaches the point where it needs to go and automatically takes the sample and retrieves it. I don't know if you all have perhaps worked on something like this or if it's just talk, but indeed we can discuss it next time, God willing, inshallah. Also, at the beginning, as you may know, before we get into the fluoroscope, hopefully. Oh, is there anything else regarding the mammography? I mean, I'm trying to simplify it as much as I can. I hope it has been understood. If there is a problem, thank you, Salam. Your words are clear and sufficient. Well, thank God for His mercy. Hello? Hello, what's up, Dr. Islam? You said you would sit with me tomorrow at this time? Okay, please keep me in the loop privately so we can talk and set the appointment. I have no problem with any time. Okay, Islam, is my voice clear? Yes, Dr. Islam, go ahead. So, is this only present in mammography? Or can it be found in any X-ray machine? It can be found in any X-ray machine. And is this an additional failure? Or is it? First, it should be mandatory for something to be present, especially with all modern machines, to prevent interference. In case a problem occurs with the machine or something happens that requires termination and reinstallation of the machine. This is more relevant with recent machines, and some machines have something called automatic brightness control, ABC. It takes this name, automatic brightness control, not just automatic like a photo timer. How? Photo timer. The automatic exposure control or automatic brightness control adjusts automatically, not manually. For example, when we talk about CT, computed tomography, is it adjusted automatically? No. I mean, for example, when we talk about the CT, for instance, we will find that we are taking a scan, for example. This scan is what we work on. There is an option in the devices called automatic exposure control. This is exactly what we are talking about, but it does it in a different way. What does it do? It takes a scout and calculates what you want to work on, for example, the chest without pillows. It starts by analyzing each pixel and its attenuation level. Then it says, I will adjust the milliampere, meaning I will give the chest. In this area, there is no high attenuation, so we set a low milliampere, while the abdomen is set slightly higher. For the biopsy bone, we set a higher milliampere. We start by making a change in the milliampere for the scan, and this is automatic. You do not control it or enter a specific value. In terms of mammography, pixel size is essential. The pixels I will use in the matrix need to be small enough so that I can achieve the best resolution. This is important. If your pixel size is large, it doesn't just affect the pixel size, but also the number of bits, or the bit depth we were discussing, which relates to dynamic range. Remember when we said that I can reach a certain number of bits within the pixel? It needs to be high. The image matrix's highest quality is represented by the number of line pairs, which relates to the MTF we discussed. You will find that it can reach about 12 line pairs per millimeter, and the number of bits can also reach around 12 bits per pixel. The number of pixels in the image itself will be approximately 1024. So, even to take a single image, you will find the image value is very high, but ensure that the model will be very high in breast images. Does the house dip reach a number of 12? Yes, it reaches a number of 12, but this is in mammography. I want to confirm the value that you find present. 1 second, can it display all these details? No, of course there is nothing. You can display completely. There is nothing. You won't be able to display everything. Because there are limitations with the display monitor, you cannot display everything, but you can display the maximum possible number of pixels. That's why you will find that mammography images are displayed on screens. specifically designed for mammography. For example, the specifications of these screens will tell you the resolution in megapixels, and you will find that the number is very high and the size is large. The luminance will also be specified in candelian per mm2. All of this is important for the display screen, especially for mammography, because your resolution is the highest, which is 1024 x 1/24, and the highest matrix size is indeed 1024.
1024, and there's nothing higher than that, right? The maximum is 1024, correct?
I apologize, but the problem with the sound is due to my internet issue. I don't know if there's a problem with Dr. Henny or if it's just me. Well, thank you for your comments. Honestly, there are questions from you. I got disconnected, and I think you did too. All right.
Dr. Salama to you.
Thank you, everyone. Dr. Islam, if you please, a question about radiation protection. Okay, doctor, it emits
The lecture was from Dr. Wahida, and we finished. But if you need anything, I am at your service. Just don't stress too much. Peace be upon you.